Hello everyone, welcome to new class. Today's class is the continuation of op-amps. So next is the applications of op-amps. First one is phase changer. So this is a circuit for inverting amplifier. The inverting circuits implemented with an op-amp are more constant and distortion is comparatively lower and provide a better transitory response. So here we are discussing about inverting amplifier. Both inverting and non-inverting amplifiers can be used, but the importance of inverting amplifier is the op-amps are more constant with inverting amplifier and distortion is comparatively lower and provide a better transitory response. So let us discuss about this phase changer. So this is an inverting amplifier circuit. So here RF is the feedback resistor and R1 is the input resistor. So in this figure, if R1 is equal to RF, then what is the output voltage of inverting amplifier? So it is minus V in into AF, where AF is equal to V0 is equal to V in into AF and AF is equal to minus RF divided by R1. And here if R1 is equal to RF, then the gain, that is AF is the gain, and gain will be equal to minus 1, that is unity gain, and the sign of the input signal will be changed at the output, that is V0 will be equal to minus V in if R1 is equal to RF in this inverting amplifier circuit or amplifier circuit with op-amp. So in this case, that is V0 is equal to minus V in, that is the sign of the input signal will be changed at the output. Such a circuit is called phase changer or phase inverter, also called phase inverter. So this is phase changer circuit, that is here the unity gain, that is gain is unity in this case. So the output signal V0 is equal to minus V in. So this is phase changer circuit. Next is scale changer. Here if this ratio, that is RF divided by R1, here RF divided by R1 is equal to K, that is a real constant, then the closed loop gain, that is AF is equal to minus K, that is AF is equal to minus RF divided by R1. So if RF divided by R1 is a real constant K, then AF will be is equal to minus K, and hence V0 will be equal to minus K into V in, that is the input voltage has been multiplied by a factor minus K at the input. So this is called scale changer. Next is summing amplifier. In this circuit, the output is the sum of several input signals and it may be inverting or non-inverting. Let us discuss about inverting summing amplifier. This is the circuit for the inverting summing amplifier, and here there are three input voltages V1, V2 and V3, and R1, R2 and R3 are the 3 input resistors and RF is the feedback resistor. Then assume ideal op-amp. So ideal op-amp means VID, that is zero offset voltage, that is difference input voltage VID is equal to 0. VID equal to 0 means inverting and non-inverting voltages are equal. That is, here the non-inverting input terminal is grounded. Then the voltage at node A is 0 to make VID is equal to 0. So we can write the nodal equations at point A. So at node A, we can write this is sum of these voltages. So at node A, here V1, V2, V3 are the 3 voltages. So we can write the current like this, that is V1 divided by R1 plus V2 divided by R2 plus V3 divided by R3. These are the 3 input currents towards this point A. Then we have to write plus V0 divided by RF is equal to 0. So from this we can write V0 divided by RF is equal to minus of V1 divided by R1 plus V2 divided by R2 plus V3 divided by R3. So we can write output voltage V0 is equal to RF divided by R1, that is minus of RF by R1 into V1 plus RF by R2 into V2 plus RF by R2 into V3. So this is the output voltage in inverting summing amplifier. And what is the output voltage in inverting amplifier? So in an inverting amplifier, V0 is equal to minus RF divided by R1 into V1. And in the case of many inputs, we have RF divided by R1 into V1 plus again RF divided by R2 into V2 plus etc. And here there is minus here. So this is in the case of inverting amplifier. So the output is inverted and weighted sum of the inputs. And in special case, when R1 and R2 and R3 are equal to RF, that is, if R1 equal to R2 equal to R3 equal to RF, then what will be V0? Then V0 will be equal to minus of V1 plus V2 plus V3. So if R1 equal to R2 equal to R3 equal to RF, then we will get V0 is equal to minus of V1 plus V2 plus V3. In which case the output V0 is inverted sum of the input signals. And also there is another case, that is R1 equal to R2 equal to R3 equal to 3 RF. So when R1 equal to R2 equal to R3 equal to 3 RF, then what will be V0? V0 will be equal to, so here we will get R1 is equal to 3 RF, that is RF cancelled, and in the denominator we will get 3, that is minus of V1 plus V2 plus V3 divided by 3. So if R1 equal to R2 equal to R3 equal to 3 RF, then V0 will be equal to minus of V1 plus V2 plus V3 divided by 3. That is, the output is the average of the input signals and also inverted. So this is the case of inverting summing amplifier. Next is non-inverting summing amplifier. So this is the circuit for the non-inverting summing amplifier. Then consider ideal op amp. So let the voltage at node A is VA. Then the voltage at the inverting input will be also VA. So the nodal equations at node A can be, node A is V1 minus VA divided by R1 plus V2 minus VA divided by R2 plus V3 minus VA divided by R3 equal to 0. Then we can rearrange this one, that is V1 divided by R1 plus V2 divided by R2 plus V3 divided by R3 equal to, here this one we can take the other side. So VA into 1 divided by R1 plus 1 by R2 plus 1 by R3. So from this we can write VA is equal to V1 by R1 plus V2 by R2 plus V3 by R3 whole divided by 1 divided by R1 plus 1 by R2 plus 1 by R3. In the case of non-inverting amplifier, we have V0 is equal to 1 plus RF divided by R1 into input. So here input is VA. So we can write V0 is equal to 1 plus RF divided by R1 into VA. Now we can substitute the value of VA in this equation. So V0 is equal to VA into this one, that is 1 plus RF divided by R1 into VA. And here what is R1? R1 means this resistance, that is the resistance at the inverting terminal. So here it will be R. So 1 plus RF divided by R is the gain of the non-inverting amplifier. Then into this VA, that is V1 by R1 plus V2 by R2 plus V3 by R3 whole divided by 1 by R1 plus 1 by R2 plus 1 by R3. So this is the output of summing amplifier, that is non-inverting summing amplifier output voltage. So this is also non-inverted weighted sum of inputs. So here in the case of non-inverting amplifier, output is 1 plus RF divided by R into input voltage, and in the case of summing amplifier we get V0 is equal to the non-inverted weighted sum of the inputs. If R1 equal to R2 equal to R3 equal to R equal to RF divided by 2, then we will get V0 is equal to V1 plus V2 plus V3. So to get the output voltage equal to the sum of input voltages, we have to put the values of resistors like R1 equal to R2 equal to R3 equal to R equal to RF divided by 2. That is, putting the values of R1, R2, R3 and R equal to RF divided by 2, we will get RF divided by here RF by 2. Here also RF divided by 2 is 2 divided by RF into V1 plus V2 plus V3. Then in the denominator we will get 2 divided by RF into 1 plus 1 plus 1, that is 3. So here we will get V1 plus V2 plus V3, that is output voltage V0 is equal to V1 plus V2 plus V3. So this is the case of non-inverting summing amplifier. Next is differentiator. So this is the circuit diagram for the op-amp differentiator. So as the name suggests, the circuit performs the mathematical operation of differentiation. That is, the output waveform is the derivative of the input waveform. So assume the ideal op-amp case. So here this is node N. So here this is an inverting amplifier. The node N is at virtual ground potential. That is, node N is at virtual ground potential. So Vn is equal to 0. Then the current IC, that is current IC through the capacitor, can be written as IC is equal to C into d by dt of V in minus Vn. And here Vn is 0. So we can write current IC equal to C into dV in divided by dt. The current IF through the feedback resistor is, what is IF? IF is equal to V0 divided by RF. And there is no current into the op-amp. So this is at a ground potential and current through the capacitor is C into dV in divided by dt, and the current through the feedback resistor is V0 divided by RF. Now we can write the nodal equations at node N. So at node N, the nodal equations are C into dV in divided by dt plus V0 divided by RF is equal to 0. Or we can write V0 divided by RF is equal to minus C into dV in divided by dt, or output voltage V0 is equal to minus C into dV in divided by dt into RF, that is RF into C. So we can write minus RF into C into dV in divided by dt, that is the output voltage is equal to the derivative of the input voltage. And also there is a constant minus RF into C, that is the output voltage is this constant times the derivative of the input voltage, and the circuit is a differentiator, and the minus sign indicates 180-degree phase shift of the output waveform V0 with respect to the input signal. And this is the input and output waveforms of the differentiator. So if the input is a square wave, the output will be spikes, and if the input is a triangular wave, that is if the input is a triangular wave, then the output will be a square wave. So if the input is a triangular wave, the output will be a square wave in differentiator. So that is about the differentiator circuit. And here there is a resistance called compensating resistance or comb. So what is the use of this compensating resistance? To cancel any offset voltage caused by the bias current flowing through the resistances, just add an equivalent resistance in series with the other op-amp input, and that is called the compensating resistance. Next is integrator. So this is the diagram for integrator, and in the differentiator, if we interchange the resistor and capacitor positions, then we will get integrator. So in differentiator, here is the capacitor and the feedback resistance, and here it is interchanged, that is here the feedback capacitor is there and this is the input resistance. Now we can write the nodal equation. So nodal equation at node N, that is V in divided by R1 plus the current through the capacitor is Cf into dV0 divided by dt equal to 0. That is rearranging, we will get dV0 divided by dt is equal to minus 1 divided by R1 into Cf into V. Now integrating both sides, that is integrating, we will get integral 0 to t dV0 divided by dt is equal to minus 1 by R1 Cf is constant, then integral of 0 to t V in. Now take this dt to this side, that is integral of 0 to t dV0 is equal to minus 1 by R1 Cf integral 0 to t V in into dt. That is here the derivative of dV0 is V, that is V0. Then applying the limits, V0 of t minus V0 of 0 is equal to minus 1 divided by R1 Cf, then integral 0 to t V in into dt. So here we can write the output voltage V0 of t is equal to minus 1 divided by R1 Cf integral 0 to t V in into dt plus V0 of 0. V0 of 0 is the initial output voltage. So this is the expression for the output voltage. Thus, the output voltage is proportional to the time integral of the input, and R1 into Cf is the time constant of the integrator. And here also a resistance called compensating resistance or comp, which is approximately equal to R1 is usually connected to the positive input terminal to minimize the effect of input bias current. And this is the input and output waveforms of the integrator. So if the input is square wave, then the output will be a triangular waveform. So that is about some applications of op-amp. There are some more applications related to op-amp and that we will discuss in the next class. Thank you for watching the class. If you like the classes, please like, share and subscribe my channel.